All right, I'll talk about my research today in two parts, both related to SST variability in the Western North Pacific as a precursor to El Nino development. The first part is on how this one-year lead relationship is expected to evolve with future warming. These are SST and surface wind anomaly composites from CSM2 to see how the conditions leading up to a stronger future El Nino preceded by a cold WNP 1 year prior vary from that of a historical one. We see a stronger SST anomaly dipole during the WNP phase. We see strengthened summer westerlies in the western equatorial Pacific. In fall, the SST anomalies and surface convergence are stronger in the central Pacific with warming, and the warm pool extends further towards the eastern Pacific by the following winter to produce more of an EP-type El Nino. In contrast, looking at the CMIP6 composites, a strengthened Western Pacific warm pool is observed with future warming during an El Nino, but as with the CSM composites, the summer westerlies in the Western Equatorial Pacific are stronger for the SSP scenario, and the maximum positive SST anomalies and surface convergence in fall also occur in the Central Pacific. So regardless of the patterns of ENSO diversity between the two models, they agree that the conditions leading up to an El Nino become stronger with future warming, with a Central Pacific focus just prior. To further break down the effects of warming, we separated the frequencies of stronger versus weaker future El Ninos under WNP influence with warming, and we did this within each scenario using a conditional probability approach. Overall, the frequencies of stronger future El Ninos increase with warming, and the frequencies of weaker future El Ninos decrease with warming. These trends indicate that warming makes the transition to ENSO easier when WNP SST variability is introduced. Because of the effects on the upper ocean, SST budget analysis was used to break down the distribution of heat in the mixed layer, and we will look at some of those terms. These are the Ekman heat advection plots. In the spring to summer prior to an El Nino, an anomaly center of Ekman heat convergence develops from the central to eastern equatorial Pacific, where it strengthens and expands further west in the seasons leading up to an El Nino. And these patterns are stronger in the SSP scenario compared to the historical ones, and also consistent with the timing and location of the maximum positive SST anomalies in the Central Pacific with future warming. And looking at this difference between the two El Ninos, we see this zone of strengthened convergence surrounded by a zone of strengthened divergence. With westerly wind anomalies of varying wind speeds, wind stress curl anomalies can promote convergence around the Central Pacific, but divergence just away from it, which promotes southward transport of warmer water towards the Central Equatorial Pacific from areas of upwelling to downwelling. Overall, this supports stronger advection of warmer water towards the Central Equatorial Pacific under WNP influence with warming, both meridionally in this way, but also zonally by westerly wind stress. The positive entrainment anomalies here in red show how much heat enters the mixed layer from below, and we have positive basin-wide anomalies in the equatorial Pacific prior to an El Nino for both scenarios, but the impact of future warming on entrainment is to shift the stronger thermocline anomalies towards the central to eastern equatorial Pacific and promote eastward expansion of the warm pool during an El Nino under WNP influence. These histograms show frequencies of all El Ninos preceded by summer westerlies in the western equatorial Pacific. And generally, we see a shift towards higher frequencies with warming associated with summer westerlies. At the center of it all are these westerly wind bursts that can promote advective feedback by affecting Ekman and geostrophic advection and favor more of a CP-type El Nino. But they can also promote thermocline feedback by inducing downwelling equatorial Kelvin waves that can propagate thermocline anomalies further towards the eastern Pacific and favor an EP-type El Nino. Because the WNP influence with warming can strengthen both mechanisms, the ENSO diversity would likely depend on their relative strength, which can also be affected by other factors such as the background state. The second part of this work is related to a same-signed SST anomaly propagation from the western North Pacific that persists for 3 years before terminating in the central to eastern equatorial Pacific just prior to an El Nino. And we suggest that this propagation is related to the dynamics of a southeastern part of the North Pacific subtropical gyre. The surface temperature and surface currents correlation with a warm WNP phase show that the warm signal propagates for 3 years and the relative vorticity is conserved during the propagation for both warm and cold anomalies. Correlation with SST budget equation terms show strengthened Ekman heat convergence and stronger positive entrainment 3 years after propagation, conditions that are favorable for an El Nino.